Science, and you should be thinking you're at Science Colloquium today. And just a couple things as we get started. Science Colloquium, we are here on Wednesdays from 3 to 4, and I just want to touch base with you guys next week on February 11th, my birthday. I'm just saying that because it's the Darwin Day talk, and I'm a big fan of Darwin, so that's exciting. Dr. Debbie Bolter coming to talk about my anthropology researches in South Africa. And so that will be Darwin Day next week. And then also coming up on February 27th, if you ever come to Modesto Area Partners in Science Talks, we'll be in Sierra 132 on February 27th. And that night we're going to have William Duros from the National Oceanographic and Atmospheric Association speaking on the marine sanctuaries, kind of the national parks of our coastlines, and so we'll have that on the 27th. But today we have Ruben Willmarth to talk he's going to be talking with us today on heat pumps and how they work, making sure I know what's going on here. And Ruben has been working in the engineering, construction, and manufacturing industries for 15 years. His career started as an HVAC engineer for TMAD engineers in Ontario, California. And when I read this, I was like, oh, I grew up there. So that's down in Southern California. After graduating with a degree in mechanical engineering and technology from Cal Poly Pomona, and Ruben's also the only other person I know that lives in this area that has a degree from Cal Poly Pomona. Everybody else is a San Luis person from the Central Valley.
A rare breed.
Yeah, and before that, he was a student here at MJC. He later worked for both a commercial HVAC and power generation design build contractor for 6 years prior to joining the Mitsubishi Electric in 2005. Ruben's experience in commercial design and installation includes schools, hospitals, multi-story office buildings, and industrial process cooling, including mid-sized data centers. In addition to HVAC, he worked with cogeneration, biogas generation, standby power, energy studies, and solar hot water systems, and other integrated aspects of systems and design construction. Ruben is currently a member of ASHRAE and is the Western Regional Sales Manager for Carrier's newly expanded ductless and VRF group.
Mm-hmm.
What's VRF?
Stands for Variable Refrigerant Flow.
All right.
It's a commercial heat pump.
And I bet you're going to tell us more about that.
A little bit, but
okay.
Yeah.
All right. So I'm going to leave you to it.
All right.
To read.
So hook me up.
All right. There you go.
Fantastic.
And will you guys join me in giving Ruben a warm welcome? Thank you.
Well, thank you. Thank you for coming out and taking the time to talk about the wonderful world of heat pumps. I find them extremely interesting, and I'm hoping that after this you will too. So, without further ado, what we're going to talk about today is what are heat pumps and why do we care about it? You got to know the why as well as the what, right? How do they work? What kinds of them are there out there? What makes them so efficient and why they can actually be over 100% efficient, if you can imagine that. And yes, I'm taking physics. So the traditional versus modern heat pump, what's the differences between them? How they're even safer still, and why heat pumps are good for the environment and for the utility as well, the local utility. So a little bit about me. I didn't realize she was going to read my whole bio there, but as I said, I am an MJC graduate and in MET, and this actually is my first presentation on energy. My first one actually was in the public speaking class I took, and so I'm really glad I took that too. It was on compact fluorescents and why they actually made sense to use. And this is when they were a new thing, and they cost about 25 bucks a pop. And so a little more than they cost now. And I still have one left. at my parents' house. That's one of those left. Made in Japan, so it was really good. And back then, MID was 6 cents a kilowatt hour, and it's about 16 and a half cents now. So it makes a whole lot more sense nowadays, because they also cost about $5 or less. So much better deal. But even back then, they made sense when you looked at the numbers of it. So like I said, I have worked in power generation and HVAC for 15, 16 years now. And so I've gotten to try a lot of different things. But the heat pumps I've always found to be very interesting because of the way they work and what they can do. So, and I do now work for a Carrier company. We are a manufacturer of furnaces and air conditioners and heat pumps too. So what are heat pumps? Well, in its most basic form, in a nutshell, it's an air conditioner that runs in reverse. That's what it does. So why do we care? Basically, it allows us to have cost savings initially. You can save money on the installation of it because there's fewer components. It allows us to do that because it's 95% an air conditioner already. There's really only a couple of components that are different. Basically a valve and a few controls. And that allows it to run in the opposite direction. You get really high efficiency operation compared to a furnace. You know, even the best furnace in the world can get you about 95%, 98%. We can get 300% or more out of a heat pump. The Modesto climate is actually very well suited for heat pumps, air source ones, and so because it rarely goes below freezing here, and that is where you get the best range of efficiency with an air source heat pump. So a lot of choices available to you. They run efficiently. It's a good spot for it. Good climate. And heat pump water heaters are a newer development. They can be a very good investment. I have one. I used to have an electric water heater, and I figured out it would be about a 1.5 year payback to get mine. So that closed the deal really fast once I figured that out. So 18 months. And of course now there are MID rebates. So heat pumps, heat pump water heaters, many of them can qualify for a rebate if they're a high efficiency unit. So that's another reason to check them out. So what kinds are there? Well, there's several basic types. There's the traditional air source fixed speed heat pump. This is the type that was developed soon after World War II, and it really is a standard air conditioner that runs backwards. There's not too much different about it. They have been around for a very long time, and some people may not have the highest opinion of them because of the way they operate. But a lot of that's changing. I'm going to get into it a little bit. There's newer types. There's the air source variable speed, or they also call them inverter driven. These have variable speed compressors. They have variable speed fans, both indoor and out, and are often available in different styles here. Into the stronger one. You have both the vertical discharge and the horizontal discharge. Many different brands, many different sizes available of these newer ones. These are what I call the modern heat pumps. So I'll refer to that later. Then there's also ducted and ductless heat pumps. So on the inside now, we're used to the traditional building with a furnace type air handler with a distribution ductwork under the floor or over in the attic, basically out of sight. That's the very common one. There's also another style that's very common in Asia and Europe and beginning to get more common here, which is the ductless style. And you can see this right here. So that has basically two components. There's a fan unit that goes on the indoor, and then it's connected to your outdoor component like this or like this. So this is actually the kind I have in my house. I have an older farmhouse, and it did not lend itself well to installing ductwork. About 2/3 of it didn't even have an attic. The space under the floor was too tight, so the ductless made a lot of sense. And I also happened to work for a company made at the time, so the employee discount helped. There's also ground source. So these are different than the previous ones, which are all air source heat pump. This one, we're actually pulling and pushing heat from the ground itself. So you have a set of pipes that are drilled into the ground or in trenches in the ground adjacent to the house. So this style needs more land definitely, but if you have it, it's a good thing. These don't need as much land, but you definitely need to be able to get a drilling machine into the property. So they are They are a little more expensive, but they also have very good efficiencies. And then, of course, there's the heat pump water heater, which is one of the newest developments. These came out just a couple years ago, and many different styles available now, several different brands, and offer some very attractive efficiencies to the user. And if you have an electric water heater already, they're a very simple change out. So how does it work? What are the basics here? So any refrigeration system has to have 4 components. You have to have a compressor, a condenser, an evaporator coil, and an expansion device. Basically, the compressor takes a gas, and compress it, it gets hot. So that's the basic physics here. When we compress a gas, it gets hot. When you reduce the pressure on it, it gets cold. Or if you have a liquid, when you reduce the pressure, it boils and gets cold as well. And the key thing to making any heat pump or air conditioner work well is the fact that we're using a gas to liquid phase change. So that makes the process much, much more efficient. So when we compress that gas, it gets very hot, and then we can remove heat from it and it condenses into a liquid. And so we reject a lot more heat that way. So this, in an air conditioner, this would be the outdoor coil. We'd be rejecting heat to the outside air. If it was a ground source heat pump, we'd be rejecting it to the water, and it rejects heat to the ground. So once that heat has been removed, all the gas turns to a liquid, but it's still a warm liquid, and we take it to the expansion device. This can be a simple orifice hole, just a hole drilled in a plate, or more advanced systems will use an expansion valve that's either thermostatically controlled, or the best ones use one that's electronically controlled. So then you can optimize its operation much more efficiently. And once you drop the pressure, then that liquid goes into the evaporator coil, and that is where it absorbs the heat. So it starts to boil the refrigerant. And at a very low pressure, it becomes a very low temperature also, and so it absorbs heat, boils away, and we start the process all over again, going back into the compressor. So for an air conditioner, this is always the indoor, that's always the outdoor. For a heat pump, these can reverse. And so basically there's a 4-way valve that allows these to reverse operation, and it runs in the backwards direction. So why are they so efficient? A typical heat pump can be anywhere from 200 to 400% efficient. And we're not breaking any laws of physics here. And it's because what happens is we move heat. We are not creating anything more than we have electrical input for. That's required by the laws of physics, but we're also moving it in the process. And so that is what lets us get the higher efficiencies. So 1 kilowatt in of electricity generates 1 kilowatt of heat in the process through the motor, and then we move 2 more on average, and then we end up with a total of 3. So you got 3 kilowatts out for 1 kilowatt in the form of heat. And that's what makes them so efficient. And that's what makes them a really neat and exciting thing. I remember reading about these in physics class when I first came here, and just thought it was a cool concept back then. And I wished I had one in my house because my bathroom was super, super cold in the wintertime. But now I do. So, another nifty trick, if your power plant, as any modern combined cycle power plant, like the one that MIT has over on, I can't think of the name now, but right down the road here, the second power plant they built is actually a combined cycle plant. And it's 80 megawatts, and it's about 50% efficient. Now, on average, they can be in the ballpark of 50%. So if you use that as your rule of thumb, and you have 300% efficiency with a heat pump, you end up with a net of 150% efficiency on the gas that you burn. Whereas in a furnace, the best you can do, any combustion product, about 95% or so, 98% maybe. But we can actually get 150. So that's what's really cool about it. So it makes it a much more economical use of natural gas and other resources. And with heat pumps, very similar effect. We get about more than double the capacity of a traditional electric water heater. Most of those are about 0.9 to 0.93. They call it the energy factor, which accounts for the energy it takes to heat the water, which is about 100% efficient on a heating element, like one of these. But then you have standby losses, so the heat comes off the side. So a really well-insulated tank will get you about a 0.93 energy factor, but a low-end heat pump water heater will get you 2, and a really good one will get you 2.75. So much more heat out for the energy you put in. And that's why it was such a no-brainer for me to replace mine with a heat pump water heater, because it ended up getting me about an 18-month payback. Now, if we compare it to like a gas water heater, you're looking at about a 0.58 to a 0.6 energy factor for your traditional gas water heater, just a standard flue. And if you have a really high efficiency condensing type water heater or tankless style, those might be 0.8 to 0.95. And your operating cost for electric here in Modesto is somewhere in between those two. So if you have a traditional type, it's probably cost a little bit more to operate. If you have a high efficiency tankless or high efficiency tank style, it'll be a little bit less. That's with natural gas at about $1.50 a therm. But if it's propane, it's going to be a lot more expensive. So the heat pump water heater is going to be a good deal for you. The only trade-off with heat pump water heaters that you need to consider is the recovery time. They don't have as fast a recovery as gas water heaters or standard electric, although they're getting better. So the first ones came out were about twice as much. Now they're getting a little higher capacity, and so they're shortening that down. But, so look at that for the size. But they do work well. I have 5 people in my house, and we had a 40-gallon electric before, and I have a 45-gallon heat pump now, and it still works fine. So, although I think when the kids become teenagers, it might not. So we might have to reconsider that, up the size of it. So, let's look at the difference between your traditional heat pump and the modern ones. The traditional ones had a fixed speed compressor, and so you had basically on-off capacity control. When the unit turns on, it runs. When you get to your temperature set point, it turns off. Very simple. But they don't work well at the lower temperatures because they can't compensate for that lower ambient temperature. And so in some cases, they needed to have backup heater strips, which is basically a toaster element in the ductwork that would supplement the capacity of the heat pump. And they still work pretty well in the Central Valley. I've had 2 of them. I lived in Rancho Cordova for a while, and that had a heat pump. That worked fine. When I was in college, my first apartment there, that had one as well. That one we couldn't tell if it really worked or not. We had to put our hand in front and let it wait for a half an hour and see if the temperature went up. That was about the only way we could tell. So that one wasn't so good. And that's why some people don't have a very good opinion of heat pumps, because that's the experience they've had, is with a poor quality one, an older one, didn't provide very warm supplier temperatures, and so they didn't feel it was very comfortable. May not have been sized properly either, so that's another factor. But like I said, when they're properly sized and installed, they do work fine here in the Central Valley. And the one I had in Rancho Cordova, it will work just fine. But your modern ones, they have a lot more bells and whistles, and these are what make heat pumps really exciting now. So the biggest single change is that they have the inverter-driven variable speed compressors. So that allows them to ramp their capacity up or ramp it back down. So depending on how much load you have. So they can provide a continuous amount of cooling or heating and be much more comfortable, as well as, because you're running a part load, more efficient as well. And I think that's probably the biggest single change in heat pumps and air conditioners in probably a decade or 2. Really big change. The part load, of course, gets you better efficiency. It also allows you to get to back off if the temperature is high. You need just a little. But by the flip side, when it gets very cold outside, they can actually speed up and go faster than a traditional compressor. And so you're compensating for the lower temperatures and keeping your heating capacity up. And you combine that with variable speed fans on the indoor and the outdoor, it makes for comfortable operation throughout the year in many climates. So there are now a couple of heat pumps that have been out for a while that can operate down to 13 degrees below zero. Not that we run into that very often here, but for places where it does, it's a really big deal. And now there's even one on the market that can operate down to 22 below zero. And that's an air source heat pump. They're still pulling heat out of the air at 22 below. So it allows them to operate still efficiently but effectively and not have to have any of those toaster heat strips that suck up your energy. So it keeps the efficiency high. So, and they're now safer, even still. All systems, I want to stress, are reasonably safe. You know, we have a lot of safety equipment built into furnaces and into heat pumps, and so they're all very good equipment, but the thing about heat pumps is they're electrically operated, so we eliminate combustion as part of the process. So there's a couple of failure modes that get eliminated. Number one, we don't have any combustion byproducts, so there's no carbon monoxide potential at all. So that's a big deal. They do run electricity, but so does a furnace, so there's really no difference there. You got the same either way. And then of course, because we're not using natural gas or propane fuel source, then we don't have any risk of fire from a leak or explosion if there's an unfortunate leak. So all of those scenarios are eliminated by a heat pump. So it's a big deal. So it's just one evolution in the way we heat our houses, and can make them even safer still. So they're good for the environment and for the utility. Because there's no combustion, we don't have any carbon monoxide in the air. We don't have any nitrous oxide either. That's another byproduct of any combustion device. Now, newer ones have low numbers, but there's still some, always. And another big deal is that because of the efficiency, we're reducing our global warming impact. And the modern ones use a refrigerant called R410A. Pretty much everybody uses it now. That has no chlorine, and so there's no impact on the ozone. So in fact, I read recently that the ozone hole is starting to repair. So that's, as the old ones got phased out, then that damage is being undone finally. There is, however, a global warming impact of the refrigerant itself. So R410A does have a global warming impact. It's only if it leaks out, so as long as it's in the system, there's no harm. But how many people here have an air conditioner in their house? I don't think I see a single one that does it. Oh, one, here we go. So, so almost everybody. So if you have an air conditioner, you have that same refrigerant already. So it's, and you're that far from having a heat pump as well. So remember, it's just that 5% of components. But the thing is that we're getting to use the same components, we're using that same refrigerant for the heating as well as the cooling, and so there's no net increase of impact there. And the nice thing is, there are new refrigerants, and so maybe over the next 10 years, 20 years, we might see newer ones get phased in that are based on new chemistries that have even lower global warming impacts. Some of these are synthetics, like R32, 1234, YF, and ZE. So there's a lot of discussion going on about those right now. And then there's even some natural refrigerants, like carbon dioxide and propane. Now, the natural ones have a lot of attraction, however, they have some trade-offs too. Propane is very efficient. I've heard as high as 40% more efficient. However, because it's very flammable, fire marshals don't like it much. And so it's limited to very, very small applications, like vending machines and such. A lot of those now use propane. But, and then CO2 is a popular one for, over in Europe for, what do you call it? Display cases, commercial refrigeration display cases. And it offers some efficiency benefits. It's also used for heat pump water heaters over there as well. So because of the higher differential temperature, it tends to have a higher performance. In air conditioners though, in heat pumps for comfort heating, they don't seem to work as well. So again, that's why we're looking at some of these other models here, the R32 and the other ones, as a potential replacement long term. But already it's an improvement because by using the heat pump with that refrigerant, you are reducing the amount of fossil fuels used, and so therefore improves the total CO2 produced. So one other benefit is that heat pumps have a lot of impact on the utilities, and air conditioning especially has a very disproportionate impact. So, for example, statewide, commercial cooling and ventilation has about 25%, uses about 25% of the energy that commercial buildings consume. So you can see here, this sliver right here, about 1/4, so that's the amount of consumption, so kilowatt hours that they use. But when you look at the power demand, it's actually over half. So if you look at this slice here, over half of the power demand is coming from air conditioning, but only 25% of the power consumption. So it's a disproportionate impact on the utility. And if you look at the total grid, you can see the same thing. This one's a little fuzzy, I know, but you can see the temperature rising and falling throughout the year. And when it's high, the power demand gets really, really high. And yet when it's low, over here and here in the wintertime, power demand is much, much less. So we've actually got a 2.4 differential between it. Or statewide, about 60% of the peak demand is air conditioning. It's a very, very big impact. And so what we have to do is we have to build generators, we have to build transformers, transmission lines, distribution lines. All of that infrastructure has to be built to support this peak demand right here. And yet we only use it a small amount of time. And so by using a heat pump, we're upping that consumption in the wintertime. So heat pumps use electricity for both the cooling and the heating. And so that same infrastructure is what we're using. So we're supporting and using that infrastructure twice as often. So what ends up happening is we're dividing that cost out over a greater amount of kilowatt hours. It's the same thing here in MID. Our peak demand is 653 megawatts, and yet 90% of the time it's 400 megawatts or less. You can see on this chart here that over here is the 90% line, and most of the time we're in this range here, somewhere between 220 to 300 megawatts of demand in the MID area. And so adding a few heat pumps on this end wouldn't change this end because this is air conditioning, but it would increase this. And so all that investment we made in the infrastructure gets apportioned out more. And so your cost per kilowatt hour comes down because of it, at least for the transmission and distribution parts of it. So, and one other benefit that heat pump water heaters have on the utility is that some of them come with a built-in ability to do demand response. The one I have has a little Ethernet plug right on it, and it allows it to plug in, and once MID has the ability to do so, then they can actually send out a signal and say that it's really high demand this afternoon, and so we need to back off a little bit. And so it just sends a simple signal, and so instead of running to maintain, say, 130 degrees, it'll back off to 110 or 100 and say, I'll hold off. And that's fine, because you have a big storage tank full of hot water, and especially in the afternoon, it's typically just hand washing or just maintenance only. So you won't even miss it, but it allows them to use that storage in the tank to help ride out the summertime peak and get to the other side of that peak curve. So that ends up being a much, much lower cost option than having to fire up a peaking power plant, or worse yet, build one. So that's something that's built into many of the new ones. Like I said, mine came with it out of the box, and so it's a feature that's there as soon as the utility is ready to use it. So, in conclusion, with good heat pumps, we can reduce total energy use, we can reduce the cost of that energy, so it's a win-win for sure, and we can improve safety and the environment at the same time. And because a lot of electricity is produced locally through hydropower and solar as well, we can even become more energy self-sufficient as well. Any questions? Yes, sir.
Can you explain how you're transferring energy to the heat pump?
Yes, absolutely.
Would you please repeat the question?
Oh, yes, the question was, could we explain how we're transferring energy with the heat pump? So from the indoor to the outdoor? Okay, yes, let me go back to that slide. There we go. So you have two heat exchangers. So this is in air conditioning mode, this would be the outdoor. In wintertime mode, this would be the indoor. So right now in the wintertime, this is your indoor coil. And you have a fan blowing across that coil. And so it's warming the air that goes across it. And then outside, you have the evaporator coil. The refrigerant is coming through and it's absorbing heat from the outside. So we're running air across that coil as well. And it's actually cooling the outdoor air. And we're absorbing heat and then taking it into the compressor, and that compressor raises the pressure very high, and so that raises the temperature at the same time, and that's how we get the heat on the indoors. So we raise that pressure, reject the heat indoors, bring it back to this expansion device, drop the pressure, take it outdoors, suck the heat from the outside, and bring it all back around again in a circle. And because we can move it, and we also get the heat from the compressor too. So there's always electricity to run the compressor, and that heat gets put into the refrigerant and into the space.
Does that process still work in just a traditional air conditioning unit?
Yes. It just, in air conditioning, it just runs in the opposite direction. So in the summertime, this is outdoors, and that's indoors.
You're basically just capturing the ambient heat.
That's right. Capturing ambient heat and then bringing it indoors, and just use electricity to run the compressor to do that.
Thank you.
No problem. Sir, you had a question? Oh.
How much would it cost to introduce a heat pump system in the standard house, which has an air conditioner, which runs on electricity, and has a furnace which runs on gas?
It wouldn't be much. It would actually probably be less if you're already replacing the system at the time. Oops, sorry.
Wow.
There we go. That was too close. So the question was, how much would it cost to put in a heat pump for a house that already has an air conditioner and a furnace already? And basically, if you're already changing that system, it would probably even be less cost than replacing with a furnace and an air conditioner, because they're two separate components. And the heat pump, like I said, is 95% of the same components. There's just a few little changes on the outdoor, and the indoor is just the fan and the coil. So, which you'd have anyway for an air conditioner. So we eliminate the heat exchanger for the furnace. So it's typically cheaper to put that in. It just, if you have a perfectly good one, it wouldn't make sense, because that would cost a lot of money, and even with some pretty good savings with propane or something, you still wouldn't pay back in a reasonable time. So the key is to catch it when you're already going to swap it out. Yes?
The little room ductless room heaters, I've seen them like in Europe, like they have, like, and so they're heaters, but then are they, yeah, there it is.
Right there.
Is that a heater and an air conditioner all in
Yes.
one unit?
Yes, if it's a heat pump.
Okay.
They make versions that are cool homes,
Okay.
but most of them sold actually here are heat pump ones.
Okay, and then it'll just switch depending on
Exactly.
one heater. Oh,
Yeah,
great.
I have 3 of those in my house, so one in the middle and 2 each, one in each end.
That's
That heats up and does pretty well. Yes. Sir, yes, you got a question?
What's the cost difference between a ground source heat pump and an air source heat pump?
Pretty substantial. So a ground source heat pump, in fact, they have pretty good efficiency benefits, but they have very significant cost differences. And I don't have a good rule of thumb for that, but it's probably twice the price or 3 times the price. So, and it's one of the things where they make a lot of sense, in my opinion, in like oh man, sorry.
Step back toward the wall more.
There we go. That's the problem. I'm
They're gonna put you in.
rushing the audience here. The thing is that they make a lot of sense when you get into the upper Midwest, where you have a combination of a lot of heating hours per year, so you use it more. And then it also gets very cold outside, and so there's a big difference between the ground temperature and the air temperature. And so that's where they save a lot of money. Now, there are some here in California, and there's some that I think make good sense, but that's one thing you'd have to really talk to somebody who does it a lot and can look at your installation. And if you have a very easy to install installation, probably like this one on the left here, it might make sense. And there's also some rebates from MID for that helps with it. And I think right now, there's also some pretty good tax credits federally. So if you add all those up, it might work very well. But you do need to look at it carefully and see if you can get that investment paid back in a reasonable time. And I would actually, one thing I would look at, because we have such good climate here in the Modesto area, and it just doesn't get as cold, the differential between the air source efficiency and the ground source efficiency isn't as much. So you might get a better bang for the buck by doing an air source and spend that same amount of money on photovoltaics and end up with less total energy use. So that's why I would also look at that. Yes, sir.
It's
Seems like in California, if you replace a heater or an air conditioner, you have to have ductwork inspected.
Yes, you
Is
do.
that required for heat pump?
If it is a ductless heat pump, no.
If it's a
If
duct,
it's a ducted, yes.
that swamps the cost of any application, any appliance you buy.
It can be pretty substantial sometimes.
Yeah,
I mean,
2 times, 3 times, 5 times.
but they do it because they found cases where 30% or more of the air was leaking out of the ductwork. And so it really was a requirement that they do that. Nowadays, they have to, on a new house, it can't be more than 6% leakage rate. And if it's an existing house, they're retrofitting it, it's got to be, I think, 16% or at least a 25% reduction. So, because unfortunately, sometimes they can't get it below that. So that is a significant loss. You have a question?
In 1987, we built a home that had a heat pumps, 2 heat pumps in it.
Okay.
And there were 2 units outside and 2 pillars inside that were in
Mhm.
closets. But the source of the heating was our well.
Yes.
The well pulled it through, and then we had another well that we injected the water back into the ground table. And that
Yes.
that was the well. That last well was the one that the county was most desirous
It's
of.
injectional well, yes.
They made sure that it was, they would come at weird times to inspect and make sure it was
Mhm.
capped properly.
Yes, do you live on the north side of Modesto?
That was in Del Rio. Is that-
Yes, I know some folks up there, they had one of those too. And it was the same thing, it was 2 essentially ground source heat pumps, but that's what they call an open loop ground source heat pump. And those are frowned upon nowadays, and you probably couldn't get a permit for an injection well anymore. But they're very efficient because you eliminate, efficient cost-wise, you eliminate that whole loop and the cost of building that loop. You just have your well, and it's just, you have to look at what's the energy it takes to pressurize the water, which usually that's more than circulating the loop, but it is a
And you haven't mentioned how quiet the systems are.
Yes. Well, they vary from brand to brand, but they are often very, very quiet. And, that's one thing that is nice about the split system ones too, is that the compressor is outside.
I have one more question.
Oh, yeah, go ahead.
Sorry. On the water heater.
Yes.
If you put a recirculator in that system, would it be rob the efficiency if you had a house recirculator?
Any recirculator will use some heat, but if you have a high efficiency heat pump water heater, the impact is less. So because you're producing the heat more efficiently. But yeah, any recirculator will
And you're
consume.
saving water.
Exactly, yes, you're saving water by doing that. So that's a benefit for it. I have another question? Yes.
If someone is doing like a little attic conversion, adding space in their house, and they didn't want to like redo them, would it be okay like to have your old furnace serving the old part of the house and add the heat pump kind of heaters or, yeah?
I typically recommend that because usually a system that's built for your house is set for a certain size. And if it's oversized, you might be lucky and you don't need to. And that happens a lot. But a lot of times they're not. Or if you have the ductwork leakage issue and you can't seal that up enough, then you may not have enough capacity to serve that one. So if you're doing that add-on or somewhere in the house, then adding a small system like this will be a very easy way to do it. And they make several different versions. That's a wall mount. There are ones that are cassettes that go flush down to the ceiling. There's actually pancake style ducted ones that go above the ceiling. So it's still a ducted one, but it is only a few inches high, and so several different ways to do it. And if you keep it entirely within the envelope, you don't have to do that duct testing. So that's the one exemption. You can keep all the ductwork inside the envelope. Yes, sir.
What is the efficiency gained by not having ductwork? Is there a number on that?
There's not a specific one. It depends on how well you do the ductwork. And if you have that ductwork entirely within the envelope, you don't have those losses. And if you oversize the ductwork and keep the fan energy down, then the differential is less. But in general, when you have a ductless like that, you're always going to save energy because your air path is from here to there. And so that's the least amount of energy that's possible typically. But I've seen some of these, will use 30 watts, and a similar one like this would use 60 watts. But your average house will have a fan motor that uses 500 watts or more. And I had one, my second house had about a 800 watt fan motor. it was a whopper. Yes, sir.
Those units that you show on a wall, is there a supply and return built into it?
There is, yeah. If you see that slot right there,
Yeah.
that is the supply.
Yeah.
And then at the top of the unit, that is the return. So it's pulling air from the top of the ceiling. Sometimes there'll be slots in the front too, but air comes in the top and then out the bottom. And so it blows the cool air or the warm air. Usually cool air will blow across the room. Warm air we try to blow down to get it to mix well. Sorry, you got a question?
I'm curious, I just had complete new heating, ventilation, air conditioning done. No one gave me a bid on a heat pump.
Oh, really?
Are these just a lot more expensive?
No, it depends, but sometimes it's usually cheaper. But people are used to, what was the word, momentum, institutional momentum. They're used to doing it this way all the time, and it's easier just to sell somebody the same thing what they already got than to try to convince them to do something else. And if what they have already works, you know, it's not a bad thing, it's just that there might have been a better choice. And a lot of people don't know, don't take the time to look at what the cost differentials are. So like I said, if you're on natural gas, your costs are going to be pretty similar. If you're on propane, it's going to be significantly cheaper than on a heat pump. So I don't know which one you have, but if you want any of the other benefits, the environmental and others, then the heat pump gets you those as well. But that's not something most contractors spend much time on. So, yes, sir. Way in the
Just
back.
had the construction of a wonderful new building because of Measure E funds, thank you, community, and we're in it right now. Do you know if we have any heat pumps that are working here using high efficiency, or does the LEED rating be achieved in other ways?
Well, there are all different sizes. You know, I tend to work with more the commercial side, the larger ones, and there's buildings all over the place that use larger commercial heat pumps. I'm not aware of any right around here though. We talked to some of the local utility about one at one of their headquarters, but nothing yet that I'm aware of. Unfortunately, not yet. Although I take it back. There is one over on, I can't think of the name of the road, just off Warrensburg Avenue. There's a facility over there that uses a couple of commercial size heat pumps. Yes.
So you have a ducted system. How often should you have it inspected? Because I don't know if it has like a standard wear and tear over time, like say 10 years, you might want to have it looked so you're not losing any sort of airflow or anything like that.
As a general rule, any kind of ducted system, you ought to have it inspected twice a year, at least once a year. A heat pump, you can probably get away with once a year, but a furnace, you want to inspect it before the heating season, and then the air conditioner, you want to inspect it before the cooling season. So make sure all the coils are clean. On furnaces, you want to inspect the heat exchangers, make sure there's no cracks, anything, all the flame components are safety components are working correctly. So you really want to inspect each of those once a year. And then of course, you know, your filters, you want to make sure those are changed out regularly. So, good question. Yes, sir.
What were the gases used other than CO2 and propane?
For fuel gases or just, I'm not sure what you're asking.
For the heat pump.
The refrigerants. Yes. The question was, what were the gases used besides CO2 and propane? I'll get you back to that list. There we go. So there's R410A is the standard refrigerant used in the industry right now. Pretty much everything sold is R410A. And that is basically a blend of two refrigerants. Actually, it's 32 and 125. And so they're looking at using R32 by itself, which is mildly flammable. That's its one trade-off. And then these other two, which my understanding are not. But then they have other characteristics that, you know, I think 32 is more efficient. So they're weighing the pros and the cons of going and using one of these in residential heat pumps in the near future, probably 5 years, 10 years. And then these two, I think we'll see used in commercial applications and possibly residential heat pump water heaters. CO2 is a very, very high pressure, so I think it makes a lot of sense in commercial refrigeration, but it doesn't have the efficiencies yet for residential use. Yes, also.
Are the first three, are they man-made or are they like combined with something natural?
These are not man-made. The first three are man-made. So these two here, CO2 and propane, are considered natural refrigerants because they're naturally occurring compounds.
Gases?
Gases, yes. Mm-hmm.
So natural gas?
No, natural gas itself is not. So propane, you can find it's considered a natural refrigerant, and CO2 as well. It's not a synthetic compound. That's what they mean by it. And natural gas is just it's a common term. It really is a whole mix of gases, including propane. Yes, sir. The green shirt.
Rough idea, you say a 50-gallon gas hot water heater versus this one.
Oh, 50, okay. Gas, okay, so 50-gallon gas water heater, probably charging a couple $100, $300, $400. And a heat pump water heater, the one I got was $1,100, so it was more expensive. But I got a $100 rebate from the utility, and it was on sale over $200. So actually, I think it was $1,200 at the time. So I ended up paying $900 for mine, and I got that money back in 18 months.
Do all local contractors carry these?
I don't know that. I bought mine at Sears and then put it in myself. But I think more and more are, as there's more and more brands that are being offered, and there's education going on within the industry for that. So you see more and more. Typically, they're not going to offer it to you unless you have an electric already. If you have a gas or a propane, they're probably going to offer you a gas water heater. But if you want to switch, then ask them about it, and then they'll help you assess what the challenge will be. Obviously, when you have a gas or a propane water heater already, you're not going to have the electricity service. So you have to see what's it going to cost to bring in that 25 to 30 amp service. Especially in the case of propane, it may be well worth it. Just straight economics. And if you have natural gas, it probably has to be more for altruistic reasons, but it will cost you still a smidgen less than your standard gas water heater will, because with MID rates. Because at a 6.0 energy factor, it still costs more to run a gas water heater than a good heat pump water heater. Good. Yes, sir.
A question about MID rates of 16.5 cents a kilowatt. How does that compete with just a regular natural gas furnace in terms of heating in the wintertime? Are we cost effective or close or not at these gas
We're
prices?
in the ballpark. We're really in the ballpark. I ran some numbers last night just to check and see what the latest was. And PG&E is running about $1.50 a therm. That's what they predict for this year. And so with a good efficiency heat pump, you're going to be right in between a standard efficiency gas furnace and a really high efficiency condensing gas furnace. So it's closer to the high efficiency one, but it's right there in the ballpark. So what your house is going to be right in that ballpark, but it's going to vary depending on your ductwork and your insulation and
solar unit.
Exactly. So there's a lot of factors there. So if you can lower your fan energy, that makes you more efficient all around. I would say it's going to be very equivalent. And so if you're going to change them both out, you can probably end up saving money up front by having just a heat pump as opposed to a heat pump and a furnace.
I've encountered some resistance from heating and air conditioning companies to install something like this because they're new maybe, or they're new.
The ductless one or the standard?
The ductless one.
Yes.
And they also aren't as profitable, it seems, in terms of installation. Or is there a conflict of interest?
I know that's not true. Some may believe that is the case, but I have seen people run the numbers, and for a contractor, this is more profitable, even if he's making less per unit because it's more efficient to install. So he can have more installations with the same number of man hours in a year. So it comes down to, you have a certain number of people working and they can do so much work in a year, they can get more done and end up better off with the ductless, based on the presentation I saw.
Well, but they don't get to inspect the ducts, though.
No, no. And so maybe if they do that too, then it swings it the other way. So, yeah, what I saw was prior to duct testing. But I think it's comparable enough. More than anything though, is what you're used to. And most people are used to the duct ones, and that's still what they're comfortable with, and so most of the time that's what they promote.
Can they coexist?
Oh, yeah, yeah. You can have ducted on one part of the house and ductless on another part. Sometimes what we see for ductless is you'll have a big house with a ducted system, perfectly good system, but if it's an empty nester, you may only want to heat a portion of the house. So you can have one of those put in your master bedroom. And so at night, turn the house way down and just heat the bedroom, keep you comfy. You're not wasting energy by heating the whole place. Or you can put two, one for if you always hang out in the living room, then just air condition that during the day instead of at one time, as opposed to the whole house at 4 times or 5 times. So you can save a lot of energy if you do that. So you can have them, they can overlap and save a lot. Yes, sir, Jim? Yes, yes.
I was curious, from an aesthetic standpoint of view, you mentioned something earlier. Are there models available that don't actually stick into a room like that?
There are. There's ones now you have to cut a hole in the wall, or cut a hole in the ceiling. But there's ones that can go flush to the ceiling. And my uncle had one of those in his house.
What about the return to them? You're going to have to figure out some way to get the return air to them.
Well, that one, the cassette style, that has a return in the middle. So it's a big square, and air returns in the middle, comes out the sides. And so it allows it to do both together. So this is pretty clever what we got there.
You were saying that this works pretty okay in the Central Valley. What are the lowest temperatures you can work, environments, so you can have one of these systems?
Pretty much anywhere in the U.S. So like I said, that one goes down to 22 below. And there's not too many states where it's below that. There's a few. So Nebraska, North Dakota, you still need some kind of backup to it, but that's only a few days of the year. That's the nice thing. So, and in those states, electricity is very cost effective. So you use that for your primary heat source and then just supplement with something else. Yes, sir?
I lived at 5,000 feet in Montana, and that's one of those.
That would get
those one of those places.
below 22 below, yeah.
The people there will burn wood, because they're used to wood and stuff.
Well, and frankly, you want to have, when it gets that cold, I think it's a must to have something like wood as a backup, because if the power goes out, you need something, and you cannot let the house get cold, because you will freeze to death with it. So yeah, definitely, I think it's a good idea, but when the power works, it's great. Yes, sir?
Are they working on systems that can run below the 22?
Possibly. I'm sure competitive nature, we'll probably see it 25 or 30 below eventually. Yes, sir?
If it gets that cold, wouldn't you just want to ground source everything?
Well, it makes more and more sense as it gets that cold, but you also have to look at how often is it that cold. So if it's only a couple of hours a year, like for example, Billings, Montana, I just did something on that recently. The average wintertime low in Billings is 16 degrees. And so while it gets much, much colder than that once in a while, the average is only 16 degrees. And so that's right in the sweet spot for a good heat pump.
Yeah, it's about like Reno.
Yeah. So it's just that once in a while you get that really cold blast that you got to be able to handle. But you can use something like a wood heat or a propane heater, something that it costs more to run per hour, but you only use it once in a while, and also has the benefit of being standalone. So if power goes out, you still got something. Because even a gas furnace will not operate with power out, because you have a fan, you have often a combustion blower, and sometimes even water heaters have this on them. So power goes out, so it goes away. It's we're a very connected world anymore. One second, gentleman in the green, yes.
Yeah, just a hypothetical 2,000 square foot house with ductless heating. How many of those would you have to have in a house to heat the house and cool the house of the ductless?
2,000 square foot is probably going to be on the order of 3 tons to 4 tons, depends on how well insulated. Newer houses, you could probably be down to 2 tons. There's some very well insulated houses nowadays. But usually what happens is, how many zones do you want to have? So you can have something like that. I'd probably have 3 to 4, 3 to 5. One for the master bedroom, one for the living area. And then I might have one per bedroom if you want individual control, but that's more expensive. So I might take all the other bedrooms and lump them into one zone with one low profile ducted and combine them together. And so that covers you for empty nesters, it covers you for having individual temperature, it covers you for cooling the downstairs during the day and then the upstairs at night. And if you have just a master bedroom you want to heat it, you can do that too. So it covers a lot of scenarios for 3 zones.
How about our summers, when it gets to be 107 degrees, will these work?
Oh yeah, you size it right. That's the key, you have to size it right. So we publish curves that show what capacity is and how much it derates at 107. So you get a little bit of derate, but not too bad. They're all tested at 95. Yes, ma'am.
It's like a little bit unclear to me as it says like a law, but this is that nothing is 100% efficient. So like how its efficiency ranges from 200% to 400%.
Okay, so they're 200 to 400% because we're moving heat. So what physics says is energy cannot be created or destroyed. And so that's why it's a play on words. So we have 1 kilowatt of electricity that creates 1 kilowatt of heat. So that is what I cannot change that. But because I'm doing it with a compressor instead of just a resistance element, I'm moving 2 kilowatts with the compressor from the outdoors to the indoors. So it looks like I'm getting 300% efficiency or 400% efficiency, but really it's still following physics. It's just we're moving it from the low temperature to the high temperature using that electric motor. Cool.
In your explanation, you include the energy required for the 2 fans?
Yes.
In the compressor, in the heat source and cooling source?
When we measure them, yes. So when you look at like a heat sealing performance factor, which is the energy rating of a heat pump, one that is, I think, right about 10, I think it's 10.2 is a 3 to 1. So like that. So if it says 10.2 HSPF, it's giving you 10.2 BTUs for every watt of electricity you put in. And you get 3.4.
But the watt includes the compressor and 2 other fans?
Yes. Yes, we always include the fans, both the indoor and the outdoor fan, on a heat pump. It's only about 2 or 3%, but on a furnace they don't. So when you say 95% furnace, it's really about 3% less than that, because you have electricity to run the fan as well. Good question. Yes, sir.
Is it legit to go look at some of the installations, like the one you were referring to, the one on Evergreen?
That's it, Evergreen, yes.
Do they invite people to come in and admire their system?
The outdoor unit's probably not a problem, but it's the facility for the developmentally disabled, so you'd have to make an appointment for sure.
Might wind up getting a gift certificate.
There you go. You get over that stage. Any other questions? No? All good? Well, thank you.
Talk was also televised on the internet, on YouTube, on a live stream from ASMJC, and I think one of our ASMJC students was going to, do you want to talk about that for a minute?
Yes, today's whole presentation is going to be on YouTube, so if you want to go and reference back to it. It's actually going to be on youtube.com/user/ASMJC production and that's where you are. Or you can just search at ASMJC and you'll be able to find our channel right there.
Okay. So that should have production on the back of it here? Okay. Great, awesome. Thank you guys for coming. Maybe we'll see you next.
Thank you.